We're now going to take a look at another famous experiment supporting the so-called quantum hypothesis, and that is the so-called photoelectric effect. Here we have an apparatus of the photoelectric effect. This is an evacuated tube, and I got two metal plates. A beam of light comes in and strikes this metal plate. And when the frequency of this light is above a certain minimum value, you find that a photocurrent is measured by these ammeters. That means somehow some electrons are being pulled out of this metal plate to form an enclosed loop of current. That's called photoelectrons. This is so-called photoelectric effect. What are the experimental results of the photoelectric effect? Well, as I mentioned before, it is found experimentally that the light which can cause photoelectric effect must have a certain minimum frequency or maximum wavelength. Okay, when a plate E is illuminated by light having an appropriate wavelength, it actually means a wavelength with a certain maximum value. Has to be below that maximum value, that is. A current is detected by the ammeter, and the current arises from the photoelectrons emitted from this negative plate and getting collected at the collector plate. That makes sense. There is a voltage which I can adjust here. That is the voltage difference between plate C and plate E. Right now this voltage is positive, which means the electrons, upon being yanked out of this metal plate, will be accelerated by this voltage. And I can actually reverse the polarity of that as well, so that the electrons, upon leaving this plate E, will meet a resistance. But if they have enough initial kinetic energy to begin with, then they may still have enough energy left to overcome that resistance so that they can reach the plate C and still producing a photocurrent. Now, here are some of the more detailed results of the experiment. Photoelectric results. The potential difference, if it's positive and very large, then it turns out the photocurrent will become a constant. But as you reverse the polarity and make it negative, then at some point the photocurrent will go down to zero. That makes sense, because that means that the resistance is too large, that there is not enough kinetic energy for these photoelectrons to ever reach that collector plate, so they're turned back and the photocurrent stops. So that makes sense. Now the problem here is that this maximum reversing stopping potential, delta, negative delta Vs, depends not on the intensity of the light, but on the frequency of the light. The greater the frequency of the light, the greater the potential that you have to use to stop the photocurrent. And classically, that was never an issue. It was the intensity of the light that really mattered. The greater the intensity, the greater the energy the electrons can receive, and therefore the greater energy they have to overcome the stopping potential. The frequency of the light was never an issue. But here we go again. The frequency of the light seems to have to do with the energy of the light, just like in the case of black body radiation. So again, we have a failure of classical physics in this experiment. Let's look at where it fails. First of all, there's what's called a cutoff frequency. This means that if the incoming beam of light has a frequency that's lower than that frequency, nothing happens. No matter how strong, no matter how bright that beam of light is, nothing happens. Okay? And as you increase the frequency above the cutoff frequency, of course, there will be photoelectrons. And the higher the incoming frequency of light, the greater the stopping voltage. That is, the greater the voltage that you would need to stop the photocurrent from producing. That clearly indicates that the light energy of the light being absorbed by these electrons has to do with the frequency of the light. And the second thing is, how does the intensity of the light play a role? Again, below a certain cutoff frequency, I don't care what the intensity of light is. No photoelectrons are ever produced, no photocurrent. But above that threshold, if the frequency is above the cutoff frequency, yes, you will have photocurrent, and the strength of the photocurrent, the current I, does depend on intensity. The greater the intensity, the greater the photocurrent. Well, that makes sense because the greater intensity means simply more photons are being absorbed by the electrons, so more electrons will come out. Another thing I want to talk about is so-called ejection time. And that is, when you start shining a beam of light on it, how long would it take for the photoelectrons to be yanked out of the metal plate? That is, they are ejected from the metal plate. After they get ejected, you have a photocurrent, right? So is there a time lag between the time when the light gets shined upon the plate and the time when the electrons come out, so you can see a photocurrent? That is called the ejection time. Well, the experiment says the ejection time is about 10 to the negative 9 seconds, a nanosecond. So basically, there is no delay whatsoever. However, this does not agree with theoretical calculations based on classical physics. So classically, how long would it take for the electron to receive enough energy from the light and will be ejected then out of the plate to produce a photocurrent? Well, let's imagine the electron to have a certain radius RE, and then a beam of light comes in, and the electron captures all the light over this cross-sectional area of pi RE squared. And then it accumulates the energy so that eventually there will be enough energy accumulated by this electron so it comes out of the metal plate. Let's estimate how long this process would take. First of all, what is the radius of an electron? Well, this is a touchy topic, and we're not here to do a calculation. And classically, the great physicist J.J. Thomson, who discovered the electron through cathode ray tube, made an estimation through the so-called scattering cross-section, how electrons get scattered by light. From that, he was able to deduce a certain radius, which we call the so-called classical radius of the Earth, of the electron, that is. And that turns out to be 2.8 times 10 to the negative 15 meters, extremely small, as expected. So within classical theory, this is a reasonable estimation of the radius of the electron. And we shine a beam of sunlight on it. This is a typical intensity of sunlight, 500 watts per meter squared. And all this light gets captured by this cross-section, pi r squared, of the electron. And how much energy does the electron need in order to be pulled out of the metal? Well, it's typically several eV, several electron volts. But let's be general. Let's say it only takes 1 eV to do that. Okay, so with these data, can we estimate the time it takes for the electron to be pulled out? Yes, we can. The intensity multiplied by the cross-sectional area A of the electron, which is IA, that gives us the total power captured by the electron from the sunlight. You multiply this by T. That's the ejection time. That is the total energy from the light captured by the electron. The electron used that to overcome this 1 eV, the energy needed to pull itself out. And A is pi r squared, R being this. So from here you can do an estimation of T. So T is roughly equal to phi over I, and then pi r squared. And let's put in some numbers. This is 1 eV is 1.9, 1.6 times 10 negative 19 joules. I is 500 watts per meter squared. And then we have pi r squared, R being 2.8 times 10 to the negative 15 meters, and square it. If you do this calculation, you will find an astonishing result, and that is the time it takes for the electron to gather enough energy, or 1 eV, is about 1.5 times 10 to the 7 seconds. Okay, you know what? This is about 1 year and plus a couple of months. So the electron has to wait over a year for the photocurrent to get enough energy to produce a photocurrent. That is a far cry from the actual experimental value of 10 to the negative 9 seconds, right? So we have this stark conflict between theory and experiment once again. The question is, how do you resolve this conflict? Well, it turns out all these conflicts can be resolved with a single hypothesis. And that is the same hypothesis that Max Planck used to resolve the Rayleigh-Jeans crisis in the black body radiation. And that is the quantum hypothesis. What that means is that the electron will receive energy from light, not at such a slow rate, but in one gulp. Remember, the energy of light, according to Planck, is quantized, right? It comes in batches. It does not come continuously, rather it comes in batches in terms of what's called photons. So each photon will have energy of hf, depending on its frequency, and the electron would just receive this photon as a whole in one gulp. It cannot take only half the photon or one-third of the photon, whatever. So receive the photon in one gulp. That is an instant process, and that resolves the problem of ejection time. And the energy it received from the photon depends on its frequency. So therefore, the higher the frequency of the photon, the greater the energy of the electron as a result. And so that solves the problem of frequency dependency of the photoelectric effect. So how does that work out? We're now looking at Einstein's theory of photoelectric effect. That was the year 1905. So here is an illustration of the Einstein theory of photoelectric effect. Again, the light energy are coming in batches called photons. Each photon has a frequency f, and its energy is h times f, just like in black body radiation. The electron will absorb one of these photons in one gulp, and as a result, it has enough energy to pull itself out of the metal and go on to produce photocurrent. Let's say the energy it takes for this electron to be bailed out of the metal is phi. This phi has a name. We call it the work function. Okay, work function. And that depends on what kind of metal it is. So if we use alkaline metals, alkaline metals are very active metals. The electrons could be easily pulled out of the atoms, so the work function is relatively small. But it's typically a few eV for metals. So we have this work function. The electrons must receive at least this much energy before they can be pulled out of the metal plate. But if you only give it this much energy, then the electron would use all this energy to bail itself out of the metal, and upon leaving the metal, it will not be moving at all, or barely moving, and therefore it has to be pulled towards the positive collecting plate, and if you use a negative potential to stop it, it will not make it anymore. But if phi is less than the energy receives, remember the energy receives hf, right, from the photon. If phi is less than hf, that means the electron will not only be able to bail itself out using this much energy, and it will have enough energy left, K, the kinetic energy. That is the kinetic energy left by this electron. And if we have this much kinetic energy, then even if you put a stopping voltage on it, if the stopping voltage is not too high, the electron will still be able to overcome that stopping voltage and make its way to finish its trip to the collecting plate, therefore producing a photocurrent. So how do we find experimentally the kinetic energy of this electron once it comes out? Well, we can get that from the value of the stopping voltage. Let's say it takes a certain amount of stopping voltage to kill the photocurrent, and that is delta Vs. In fact, it's negative according to our textbook. The symbol is negative. So we take an absolute value. That means the magnitude of the stopping voltage. If you multiply this by E, that is the amount of negative work done by the stopping potential in order to slow down the electron. And if the kinetic energy of the electron happens to equal to this, then what does that mean? It means by the time the electron reaches the collecting plate, it has exhausted all of its kinetic energy, so it can barely do that. So if the delta Vs value equals this, then all the electrons with that kinetic energy can barely reach it. So this is the critical moment, critical value of stopping potential for the photoelectric current, and then this is where the photoelectric current goes down to zero. So we can replace K with E times delta Vs. So we have another equation we can write now, HF equals to E delta Vs plus phi. Okay, this is the Einstein equation for photoelectric effect. Very simple, yet the physics is incredibly clear and beautiful. So, can we then explain what's called cutoff frequency? This is the frequency at which photoelectrons will stop being produced. If you are below that frequency, nothing will be produced. And in experiment, when we measure the cutoff frequency, we define it to be where the stopping voltage is set to 0. So you don't have any backward resistance voltage to try to stop the current. You just make sure that the incoming light has a certain minimum amount of frequency, so the photoelectron is barely able to get ejected. And so you set that equal to 0, right? Set that equal to 0, and that will give you the minimum frequency. You see that? Because this term is never negative, so you set it to 0, that's as low as it gets, and that is as low as the frequency gets. Below that frequency, you never satisfy this equation, so photoelectrons will never be produced. So we have Fh times F minimum, this is the minimum frequency, equals phi, the work function. Or, if you use the wavelengths, then it's Hc over lambda maximum. Lambda maximum corresponds to F minimum equals phi. And that tells us what is that maximum wavelengths that you can use for photoelectric effect. And that equals to Hc over phi. Okay? Very simple algebra. Now, phi is typically given in eV, and lambda is typically given in nanometers. And therefore, it would be nice if you can write Hc in terms of eV times nanometers, so then eV and eV cancel, we just be left with nanometers. Normally, H is given in joule second, and C is meters per second. And these values, in using prime SI units, meters, second, joules, they're all right, but they're not very convenient. In fact, they're kind of ridiculous, even more ridiculous than trying to measure the mass or the weight of an elephant using milligrams or micrograms. You don't want to measure something that small using such a large unit. So therefore, it is convenient for us to rewrite Hc, not in terms of meter times joule, but in terms of nanometer times eV. Let's see how we can do that. So you see, I write down Hc, first of all, in prime SI units, so joule second and meters per second, so we're left with joule times meter. Now let's try to convert it to eV and nanometers. So what I'm going to do is I'm going to divide this by conversion factors. Okay, instead of joule, I want eV. So every eV is 1.60 times 10 to the negative 19 joules. That's per eV. And then you have meters, but I want nanometers, and every meter is 10 to the negative 9 nanometers. Every nanometer is 10 to the negative 9 meters. 10 to the negative 9 meters per nanometer. So you see here, joule and joule cancels, meter cancels, you flip over to eV and nanometer, and if you did that, you get a very useful number, 1240 eV times nanometer. And I'm going to box it with a red color, and I want everybody to memorize this. How often did I ask you to memorize something in physics? It's certainly the first time I asked you to do that in 1D, and this is something you memorize because it will save you a lot of time doing numerical calculations. So again, H times C equals 1200 eV, 1240 eV times nanometer. If you use that, you plug that in, then you can easily find lambda maximum. For example, if phi equals 2 eV, okay, then what is the maximum wavelengths you can use to induce photoelectric effect in that kind of metal? That will be Hc, which is 1240 eV nanometer, divided by 2 eV, you get 620 nanometers, which is within visible light. As an example, let's use sodium. The work function for sodium is 2.46 eV. There's a table in the textbook that tells you that. And the corresponding maximum wavelengths, you can easily do this calculation, find to be about 500 nanometers, which corresponds to green light. So you can use green light or any light with higher frequency or shorter wavelengths to induce photoelectric effect in sodium. And if you go to other common metals such as aluminum, zinc, and so on, these metals will have a greater work function. And as a result, you'll find that the light in the visible light range can no longer induce photoelectric effect. You have to use a higher frequency light such as UV. So you see, the same quantum hypothesis, which is the quantization of energy of light as h times f, can be used successfully to explain both the blackbody radiation and photoelectric effect. In fact, Albert Einstein never won the Nobel Prize for his work connecting with relativity, his primary contribution to physics. Rather, he won his Nobel Prize for his explanation of the photoelectric effect along with his PhD thesis topic, which is Brownian movement.